Hi. Um, as already mentioned, I'm going to be continuing on the previous discussion and presentation with the work that we have been doing with Nikos Katsouris. Nikos is over here, so he will be helping me with any questions that I cannot answer. Thank you, Nico. And I'm going to be bringing back the neural networks, basically. So during yesterday and today, you have mostly heard about the role of machine learning and neural networks, deep learning, and how we can use lots of data to handle difficult problems. And now in the last two talks, we have switched to a different approach. We looked at symbolic methods, which are sometimes called the more traditional approaches to AI. So to answer also a previous question that was asked, symbolic methods are as much AI as machine learning methods. But naturally, we start comparing these, and we start looking at what are the advantages and the disadvantages, and there was a discussion about that before. Legitimately so. I mean, they do compete to some extent. But what I'm going to be talking about today is not so much how they can compete, but how they can work together. How can we put together a neural network and with reasoning that you heard about, and why does that make sense? Why is it useful? I'm going to be talking mainly about complex event recognition, but neurosymbolic AI methods are not restricted to complex event recognition. I'm going to be talking about this mainly because that's what we're working on, and it ties very nicely with the previous presentation. You can easily imagine, I think, how this can be applied to many other domains. And I'm also going to be talking, so a lot of the work that we're doing is actually done in this project, which is called Event Flow Project, Robust Learning and Reasoning for Complex Event Forecasting. But today, in order to keep it simple, I'm going to be ignoring forecasting for the moment, and I'm going to stick to recognition, complex event recognition. So understanding what has happened. The main motivation for the work that I'm going to be presenting today comes from what Alexandros was explaining at the end of his presentation. How do we get the stream of simple events, the time-stamped simple events that we need in order to do complex event recognition? In many cases, these simple events will come from perceptual input. For instance, images or speech or other streams of sensors. In this particular use case that I'm going to be using for most of the talk, we're talking about video surveillance. So the data comes in the form of video frames. So there is some space that is being looked at by cameras, and there is some image analysis that is happening here. And of course, you naturally can imagine that dealing with images, you do it with neural networks, right? So, and that's what we want to do because they're good at it. And what we want neural networks to do is that we want them to translate this video stream into a list of time-stamped events. So for each video frame, we want the neural network to tell us how many persons there are, in this case P1, P2, whether they're active or non-active, how close they are to each other, and at which timestamp, so basically which video frame. Once we have this information, then we can use all the machinery that Alex showed earlier to generate complex events. Like this video scene is showing us two people meeting each other. This is the complex event that we're after. So the first approach that one can imagine is, let's try to loosely couple those, the neural network that processes the video together with the complex event recognition system and get a pipeline of those two systems. So what we want to do here is that we're taking the video, we pass it to the neural network generates simple events, and then we have the complex event patterns that are described down here, and we get complex events out. And the question that comes, the first problem that we have to face is, how are we going to train the neural network? What data, what supervised data do we have? What labels do we have? So in order to train this neural network, you need labels for the simple events. So you need, for each frame, somebody to tell you whether a person exists or not, whether they're active or not. So that's a lot of labeling, a lot of manual work by people. That is not always available. In some extreme cases, in some cases, in some problems where we have a lot of data, this might be the case. So, we may be able to do it. But in many problems, this is not possible. So it's not possible to get all this data. We may also not want to do it for other reasons. One such reason is that if we do it, so if we try to train the network just to identify these simple events, we may be missing out the large goal that we have, which is to recognize the complex events. So there are many reasons why we would like to work without direct supervision for the neural network, and try to work with the labels that we have for the complex events. The labels for the complex events are fewer, so it's easier to label them. It's easier to obtain such supervision. Again, here these are just some of the reasons why you may not want to use the neural network, train the neural network directly. Now, in order to be able to use the labels for the complex events to train the neural network, we need some way to propagate backwards the loss. We need, first of all, to be able to measure the loss, and then we need to be able to propagate it backwards using the gradient descent methods and so on that we have heard before yesterday, to give the feedback back to the neural network and have the training going. If we do that, we solve many of the problems that I mentioned earlier, but I'm going to be focusing mainly on the problem of lack of data. So the problem, it's much easier to get supervision for these complex events than for the simple events. There are other reasons why you may want to do it. So in the rest of the talk, I'm going to be showing to you how we can make this part here differentiable so that we can get back propagation, so that we can feed back the loss down here to the neural network. So that's the main topic of this presentation. But it's a very important one, because if we manage to do that, then we can really bring together in a very nice way the symbolic methods, the reasoning methods, with the neural networks, and train the neural networks. And this is only one way to combine neural networks with reasoning. There are many other ways, but it has a number of advantages. I would like to pause here for a moment and ask if there are any clarification questions, anything that is not clear in what I said so far. No, I'll take silence as I understand everything, so make sure that you ask the question if you want to. So let's see step by step how we can get there. The first thing that we have to do, and Alex alluded to that earlier, is that we need to move from a neural network that provides a black or white answer, and we do that usually by taking the maximum probability of the neural network, to a neural network that provides probabilities. And we do that by having a softmax. It's pretty standard for neural networks. And if we have this, then we get probabilities for all of those simple events happening. You know, how likely is it that person P1 is active at time point 12? We get these probabilities. And if we have the probabilities, then we have the machinery, and again, Alex briefly mentioned that before. We have a number of different probabilistic reasoning methods, like one is called problog, for instance, to get us from probabilistic input, probabilistic simple events, to probabilistic output. So here we get a meeting between those two people with some probability. So that's the first step. The first step is to start working with a probabilistic reasoning method. The next step is a bit more complicated, and I'm going to be spending a bit more time and go a bit slower here. So the next thing is to try to translate the logic that we have, the logical formulae, into something that is differentiable. And one way to do that is to take the rules and translate them into these diagrams. Now, what do these diagrams tell us? They tell us what are the possible models, interpretations that you've heard from Manolis before. What are the possible ways in which this rule can be satisfied? So, and there are disjunctions. You see there are disjunctions and conjunctions here. This is called negation normal form. The reason for that is that we don't have negation in the diagram, but only in the leaves of the diagram. And at the leaves, you see the values of the different variables that we have. So you can think of those three things as variables: sun, rain, rainbow. These are three variables, and they are either true or false. So the values that they can take are true or false. So down here you see all the different possibilities. The rainbow can be true or false, rain can be true or false, sun can be true or false. And their combinations, different combinations, satisfy this rule or don't satisfy it. And what this diagram is capturing is all the different ways in which the rule can be satisfied with those variables. I hope this is clear. And if we do that, then we can start traversing the diagram and finding models. These are the combinations that satisfy the rule, and enumerating them. So the first model that you see here that satisfies the rule says is a world. So you can think of a model as one possible world, one possible situation that we can be in. So this situation says we have sun, we have rain, and we have rainbow. And this is captured by this part of the diagram, where we have all three things being true. So this is one possible model, or one interpretation, as Manolis said earlier. And you can go through that, and you can imagine how this works, and enumerating all the possible models that you can have. And in this case, there are 7 of them. This is a very simple example, of course. I forgot to mention that there is a small change here in the way the rule has been written. This is in conjunctive normal form, but basically it's the same rule that you have seen before. It's just an easier way of matching the formula to the models. So with those diagrams, what we get is a way to count the models that a particular formula or a particular theory, a logical theory, has. And this is very important. Being able to count is very important. And that's why the title talks about counting and enumeration. Now, the next step is to do this counting more efficiently. And the way to do that is to move from those diagrams that I explained earlier to arithmetic circuits. So all we do here is that we change the disjunctions with arithmetic addition, the conjunctions with multiplication, and we have in each leaf one model. And if we do that, then we start applying the operations from the leaves to the node, to the root of the diagram, the number that we get up here is the number of models. I hope this is also relatively clear. And the reason why this works is because these diagrams have some very nice properties, one of them being decomposability and another one being determinism. But I'm not going to get into too much technical detail here about why these properties are important. The nice thing that we get from these properties is that we get to get this magic number very quickly. We start with a very hard problem. This is a hash p hard problem, even harder than NP hard. And we get to something that is polytime. So this is a very efficient way of doing model counting the number of models that satisfy a particular logic. Before I get even further, again, a very brief pause to make sure that everybody is happy. Again, if you have questions, if you have things that you don't follow or you don't understand, this is the right time to do that, to have them. No? Good. Okay, I'm going to continue. So the next step, so we've done a number of steps so far. We took our logic, we translated it into diagrams, and we explained how these diagrams can be used to do model counting. But so far, we have ignored the fact that our logic has probabilities. So we need to make one step further to bring the probabilities into play. And we do that by a version of model counting which is called weighted model counting. And the version is not, this method is not specific for probabilities. It's not called probabilistic model counting. It can be used for any logic that has weights. And what do these weights look like? So here you have an even simpler formula, which says that if it rains, then it's cloudy. And down here you see that the different values that rain and cloudy can take, and each value has a different weight. We don't care where this weight comes from at the moment. But somebody has given us that it is the weight of not raining is 2, while the weight of raining is 1, for some reason. Now, if we have these weights, we get the truth table of this very simple formula. Each line of the truth table corresponds to a model. So this formula has three models that satisfy the formula, the three green ones. And for each of the models of this formula, we can get a weight for the model by multiplying the weights of the individual atoms, the variable instantiations. So we get 3 for the first model, a weight of 3, 6 for the second one, 10 for the third one, and then we get the number of models which are now weighted. So we get a weighted model count, which is number 19. So here we don't get the number 3, we don't get the number of models, but we get the weighted models. Each model together with its weight. That's why we get 19 instead of 3. And again, we can use our arithmetic circuits to do this calculation very quickly. So if you put these numbers on the diagram on the arithmetic circuit, you can very quickly do the calculations to the root of the diagram, and you get the weighted model count. And now the step from weights to probabilities is very simple. Instead of having a weight here, you have a probability. So the probability of rain is 0.8. And of course, the probability of not rain has to be the complement of that, so it's going to be 0.2. They have to sum up to 1. And if you have these probabilities, which in our case, remember, will come from a neural network, if you have these probabilities, then you can do weighted probabilistic model counting if you want. So you can count the probability of this formula being true. So the interesting part here is that we get from the weighted model counting, from a situation where we're counting models, to the probability of the formula, given the probabilities of the input. So given the probabilities of the input and the formula, we can calculate the probability of the formula. And this is very important for us. This is what we wanted. And I'm going to move to neurosymbolic event recognition again. And again, a very quick pause to make sure that this is all clear. I'm very happy about that. I hope it's true. Okay. So I'm going to be showing the neurosymbolic pipeline again with an even simpler, very popular example. And I see my colleagues laughing here. This is called the MNIST addition. This is like in all the papers about neurosymbolic AI, more or less. So why do we call it MNIST addition? Because instead of using numbers to do the addition, we take the numbers from pictures, from images, MNIST images. These are very popular images. So you see here 2 of those images, and we use a neural network to give us probabilities of the 9 different digits for each image. So for each image, we get a probability of this image being 0, this image being 1, this image being 9, and so on. So we get a probability distribution over the different digits that we can have. And we get the same for the other image. Now, in addition to those images, so this is the perceptual input, if you want, the images, or it could be speech or something else. We have the logic. The logic here is very simple. It's arithmetic addition. So basically, the logic tells us how to do addition. And we take this logic and we compile it into a diagram like the one that I showed earlier, the circuit. And the reason why this is very complex is because I want to stress that these diagrams are big, and I'm going to come back to that bit later. And if you do that, then you can calculate the probability, as I showed earlier. So given these probability distributions, you get a probability of each possible result, or the probability of the result that we know is true. So somebody in this case told us that the correct result is 8. And we get a probability for that, given the compiled logic and the probability distributions. And we compare it to the actual probability, which should be 1, because somebody told us that this should be 1, this should be 8. And we calculate a loss. And then in the usual way. So we calculate a loss in the way you do it with neural networks usually, like we use cross entropy here, for instance. But now we have this loss, and we can propagate it backwards because this is differentiable. So we can push the loss back to the neural network and tell the neural network, no, what the probability distributions that you have given me are not correct. Go and update your weights. And if you do that with a number of examples, you can train the neural network. So that's what this original picture that I showed earlier was aiming at, and we are there. So, we've done it. We have combined neural networks with logic, and we can train the neural network through the logic. Are we done? Is my presentation finished? As you can imagine, no. There is still one step that we need specifically for complex event recognition, and this is handling time. So the logic that I have shown so far is not a temporal logic, cannot handle time. It's not the event calculus that Alex was talking about earlier. This is getting time into play makes things a bit more difficult. But we can handle that too, and I'm going to show you how. One way to do it is that we could try to take the event calculus rules that Alex was talking about before and try to translate these into arithmetic circuits. So we can get basically deep programs and translate them into arithmetic circuits. Unfortunately, this is very costly in terms of memory and time. So for this reason, we opt for a different representation, which is automata. Again, Alex talked briefly about them, mentioned them before. They are not completely equivalent to the event calculus, but they're usually, in most cases, they are a superset. You can express a bit more with automata. And they are very popular. So it's one of the most popular approaches to complex event recognition, and there's good reason for that. They're very popular because you get sequences of things, and automata are very good in representing sequences of input. Here you see how expensive it gets if you try to compile the event calculus rules. And this is, down here you see the length of the sequence, and this is why time is important, right? Being able to handle time efficiently is important. There's an exponential growth in the number of, in the size of the circuit that we get. In order to explain automata and how they come into the pipeline that I showed earlier, I'm going to be switching to a slightly different use case. So instead of looking at people and how they move in space, we're going to be looking at vehicles and how they move on the road. In this example, what we try to, we have a sequence of video frames, each one showing two vehicles, the small van overtaking the big van. So this is an example of an overtake. This is just one complex event that we might be interested in. And you can imagine the use of that in autonomous vehicle systems, for instance. Now, the way in which we go about handling this is, again, we have a neural network, in this case, a convolutional neural network, which generates probabilistic output, soft predictions, and then instead of the type of logic that Alex showed earlier, I was showing earlier, we get an automaton. So this very simple automaton has 3 states, those 3 nodes, and you transition from one state to another if some conditions are satisfied. I'm not going to be focusing on these very small letters here. You don't need to read them. But what I'm trying to show is that this is a special type of automaton. We call them symbolic automata. And the reason for that is that in order to transition from one state to the other, you need to satisfy the logical formula. Yeah? So on the transitions, we have conditions that correspond to logical formulas. And we often call them guards. So these are the transition guards. Again, here we have the simple events coming out of the neural network, and the complex events will come out of the automaton. Now, it is one important aspect about automata and their use for complex event recognition is that in order to recognize a complex event, we need to arrive at this final state, the one with the two circles. This is called an accepting state. So if we arrive at this state, we are sure that our pattern, the pattern that is described by the automaton, has been satisfied. So that's what we're after. We're after automata that can get us to the right complex event recognition. So getting back to the knowledge compilation method that I described earlier, we have some examples. Notice here that the examples, so these checks and crosses are the labels. Is this an overtake or is it not an overtake? So we get labels at the level of complex events, at the level of overtakes. We don't get labels about the vehicles or their location on the lanes or anything like that. We get very high level supervision. And we have the logic of the automaton. Those guards are translated into the circuits, the arithmetic circuits that I talked about earlier. And we have the automaton. These are the pieces of the puzzle that we have. We bring in the neural network into play. So the neural network takes into video frames, takes as input the video frames, and generates again probabilities, a probability distribution for the different outputs that we're interested in, the different simple events. These are fed to the circuit. And now is the new part. In addition to the circuit, we get a transition matrix. So this matrix, if you notice, it's 3 by 3. That's because we have 3 states. So it tells us how probable, given the particular input probabilities, how probable it is to arrive at each state, to transition from one state to another. How probable it is to go from, to stay in state 1, for instance, 0.2, or to go from state 1 to state 2, 0.2 again. So we get probabilities on how likely it is to move from one state to another. Again, I need to emphasize here, these numbers have to do with this, because these probabilities are used for the weighted model counting that I mentioned earlier. So they are used to calculate the probabilities of the logical formula. I know this is getting a bit complex at this point, so if you have questions, you know. And if we have those transition matrices and we have the initial state distribution, so we knew that before this input, before the input that we received from the neural network, we were at state 1 and not at state 2 and not at state 3. That's why we have 1, 0, 0 here. With a simple multiplication, we get the next probability distribution for the states. So given the input of the neural network, we get to how likely it is in the next time point to be in each of those states. And we see, for instance, that it's more likely to be in state 3, which is an accepting state. Now, if we process the sequence of video frames in the same way, giving each frame to the neural network, using the output of the neural network to do the weighted model counting, using the automata and the transition matrices to calculate the probabilities of its state, eventually we get to the end of the video. And at the end, we get a probability distribution of being at each of the states and the probability of being at the accepting state. Now, the probability of being at the accepting state is what we're going to be using to calculate the loss. Again, we use a cross-entropy, binary cross-entropy here. We calculate the loss, and the nice thing here is that everything is differentiable. So once you get this loss, you can feed it back through all this pipeline to the neural network and train the neural network. And now the pipeline is really complete. So we get a situation where our input was difficult to handle with logical formulae, so we needed neural networks. We brought the neural networks into play, and we managed to train the neural network not by giving very detailed, very low-level supervision, but actually using the complex event labels that are much easier to get. That's why I emphasized on the data, the amount of data, supervised data, labeled data that we need. So the final part of my presentation, I'm just going to show you how and which situations this is useful. And I'm going to be showing to you the two cases that I used during the presentation, starting with the overtake instance, the overtake incident. Here we're going to be comparing the neurosymbolic pipeline, the convolutional neural network, with an automaton. The automaton actually has been learned in this case, is this automaton. So the logic can also be learned from data, right? This is what Alexandros mentioned several times before. I haven't talked about that in this presentation, but the logic can also be learned. The automaton can also be learned by data, but this is a different topic. And we're going to be comparing that against a purely neural approach, where we have a convolutional neural network and an LSTM. And these are the results that we get. We get much better performance in terms of accuracy with a neurosymbolic method. And why does this happen? We have actually run two different experiments. The experiment that I'm showing here, we take as training some videos of the same dataset. This is called the RODAR dataset. It's a popular dataset. We take some videos as training and some other videos as testing. They come from the same dataset, but they're not the same video. If we take as training and test scenes from the same video, the neural network, the pure neural network method gets close to the results of the neurosymbolic approach. But I hope that you agree with me that this is a very unrealistic situation. You don't expect your new data to be exactly the same as the data you have been trained on. And that's why it is important to have the logic. So the logic allows us to handle situations that may be a bit different from the ones we have seen in the training data. So this out-of-distribution discussion that we heard many times so far, yesterday and today, this out-of-distribution situation can be handled very well in many cases by using knowledge that we have about the problem. And this knowledge may come from people or may come from other data. And we can see here also the same situation for the video surveillance case. Similar difference between the two methods. Here we have also experimented with some methods that are combining deep neural networks with probabilistic logic. And you remember the exponential graph that I showed you earlier? They ran out of memory, so it was not possible to use them, even in a rather small dataset. So coming to the end of my talk, what did we see? I hope that I have explained to you that there are situations in which the neural networks that we have heard a lot about, and they are very powerful, can and should be combined with domain knowledge. This is when we don't have enough data, which is not an unusual situation. You know, we hear about a lot of successes of big models when we have a lot of data, but I think that the situations where we don't have a lot of data are at least as many as the ones where we have a lot of data. Situations where we naturally have knowledge, imagine medical diagnosis, for instance. How much knowledge has been accumulated over the years by those people? We should use it. And situations where the input can be handled better by a neural network, but the inference could be improved, could be enriched by a symbolic method, by a reasoning method. So I have shown to you that it is possible to do end-to-end training of the neural networks without having to give direct supervision for the neural network. And I have done that in a case that is particularly difficult because of the temporal aspect, or the fact that we have time. So we got a fully differentiable pipeline. And I have shown to you how we can get better results by doing that compared to the baselines that we have used. Now, are we done? Have we solved the problem? Can we all go home? Obviously not. There are many things that we're working on, many things that other people are working on, and many things that need to be done still. We still don't know, for instance, how we can learn from the same data the logic and train the neural network at the same time. This is a difficult thing. We still haven't completely managed to do forecasting, although this is not out of reach, I think. And there are many, many other interesting research topics that I hope many of you will work on. Thank you very much.
Thank you. Thank you very much. Questions? No question? Okay.
Thank you very much. That was very nice, very clear and comprehensive. So now on the difficult problem, on how do you create the transition graph without prior knowledge of the domain? I mean, would you go like, say, try with two states, 3 states, 4 states? And I mean, what is the intuition on how to build this transition network, the domain knowledge that you've taken for granted?
Yeah. So we have trained, one of the automatons that I mentioned has been generated using training, using machine learning. But we have done that assuming that we have, and Nico, correct me if I'm wrong, assuming that we have the input stream, right? Yeah, which is a big assumption. If you want to optimize at the same time both the logic and the neural network, and do that in a way that you end up with something meaningful, it gets a bit difficult. There are optimization methods that you can use. We are testing some of them. Ideally, you would like to incorporate some domain knowledge, not necessarily the particular automaton, but some knowledge about the problem that is easier to acquire, or even some knowledge about the world. There are many different approaches that we are exploring at the moment. Even the use of large language models for that.
There's a question there. There's a question.
Can we have, do you have a microphone?
Can we have the
Please go ahead. Does it work?
Okay. Can you hear me?
Yeah.
Great. Thank you for the presentation. If I understood correctly, in the automaton, the accept state was when a specific complex event was recognized. But in other domains, could you have an automaton that doesn't have an accept state, that simply goes through the states that represent something different, and then they also feed back into the model? So depending on the state that you're in, the processing of the neural network is done in a different way?
We haven't worked with other types of automata. There are other types of automata. For complex event recognition, I'm not sure that this would be very suitable.
Mm-hmm.
But if we have cases, if you have problems that might be interesting, we can look at them.
Okay, I have something in mind. Maybe I'll
Yeah,
talk to you later.
sure.
Thank you.
Thank you. Other questions?
Yeah, there's one over there. You have a microphone. Please go
Hi.
ahead.
Yeah, thank you for the presentation. Based on your presentation, I realized that this is a step forward for explainability in AI and deep learning. And you saw that there is a very big complexity in calculations, and I would like to ask you how you can overcome this difficulty.
Thank you for this. You actually mentioned two things that I wanted to mention in my presentation, and I forgot to. So thank you for the question. The first one is the connection of this to explainability. So it is easier than a purely neural system to get explainable results. So it is easier to ask the question, why did I get this result? But it's not completely straightforward. So you still have these big arithmetic circuits that you need to trace through, but you can't trace through them. So it is a step towards explainability and robustness verification, but it's not that we easily solve that. But you mentioned also another part that I wanted to touch upon. There is one step that has hidden complexity, and this is the compilation, the grounding of the formula, of the logic, to the graph. So this takes time, but the good thing about that is that it happens only once. You don't have to do it every time, at every step. So there is a costly part, but it happens only once. I hope I answered the question. If not, please.
A complementary question to that. Sorry for taking how big is the graph given the formulas? I mean, in terms of the literals you have in the formula, how?
So how quickly does it grow given the formula?
Yes, how quickly is it?
So if you have a number of atoms, it doesn't work as simple as that. It has to do how the atoms are combined with each other. Nico, do we have? Exponentially
the number of variables.
But it has to do with the rules as well. It's not, yeah.
The rules are eventually combined with the CNF rules. So you have one CNF rule of variables and the sequence.
Okay, exponential to the number of variables.
It's a big circuit.
So any other question?
I think Ian wanted to ask something.
Thanks for the talk, it was great. When you were comparing your method against the CNN plus LSTM, have you thought about adding some sort of pre-training in the LSTM or some other, using something like a pre-trained LLM, trying to predict the next, frame of the videos? Because in a sense, your method includes domain knowledge, but the poor LSTM has no pre-training, no domain knowledge. So, what would you expect?
I think we have done that, and Nico, we have done that, right? No, using pre-trained, we have done that using the pre-trained video data sets and so on, but it hasn't helped. because it's very specific problem. I think that's my understanding, that it's very specific. It can understand cars perhaps, but at some point it was thinking that there are cats and dogs and things like that. Maybe we haven't done it properly, I don't know what. Yeah.
I mean, you could use, hours and hours of driving and just pre-train. I didn't mean using an already pre-trained multimodal LLM or whatever, pre-trained by others. You could pre-train it on many, many hours of driving just to predict the next video frame, and then do some.
That we have not done.
Yeah. Okay.
I don't know if maybe somebody has already done it for autonomous driving.
I guess
Maybe
so. I don't know much about it. But in a sense, that might give the model more domain knowledge in a way.
Maybe, yeah. Yeah, it's interesting.
Okay, other questions? There's a question there.
Hello. Thanks for the presentation. I just thought of it right now, about the knowledge graph that you built. If there, we saw an example of rainy, sun, or rainbow, etc. If those labels are like, let's say, two people meeting, the event is two people meeting, how can you handle when there's not a gathering of two people, there's this gathering happening in 5 different spots in the video. So events to happen multiple times in the same frame. Doesn't that make the graph really bigger? Doesn't the graph have to compensate for that?
First of all, just to clarify, because you mentioned knowledge graph and I haven't mentioned knowledge graph.
I meant the graph, the middle step before the automaton.
The diagram with the models, okay.
Yeah.
This is more difficult. I understand. So you're talking about scene recognition where you have multiple events happening at the same time. Yeah. So this is for the people who are working on computer vision, they will appreciate that this is a much harder problem. It doesn't happen in the data that we have. So the data that we have are single event data. But the method should be is applicable in exactly the same way. It will just be more difficult for the neural network. And you would have. I
didn't mean about the final, the complex event. I meant about the events that the small events you make, instead of the thing that you have to have for the video with the people, that you have that there is a person, a second person, they are meeting.
The meeting is not a simple event, it's a complex event.
Yeah, the meeting is a complex event, but didn't you split that event into simpler steps?
Yes, so you have active, one person is active.
Yeah.
That's the simple event. And you can train a neural network to have multiple people.
That was my question. That was what I want to say. Let's say you have multiple people active. How does the network work when there's an enormous amount of people that are active?
Okay. Now I understand. So let's assume we have a neural net. We have a situation where in each frame we have 10 people. Yeah. And the neural network finds these people, so it tells us these people are there. That it tells us how far they are from each other.
Isn't the network limited to a certain number of events of people being active, or can it handle any people?
This network is, but we would have a different network that isn't. So we could have a different network that has multiple. But you would also need to change. In this case, you would also need to change the logic. So the logic should be able to account for multiple meetings happening at the same time.
Okay.
It's not impossible, but it just makes it more complex.
Okay. Any other question? No. I have a question. I'm not sure I got what exactly do you differentiate in the middle part, in the logical part, symbolic part. What's the objective there?
What do we differentiate?
Yes, what is the objective there and what information you pass in the neural network from the symbolic part?
We pass the loss. So we get a loss from
From
the result. So let's ignore the automaton for the moment,
Okay.
right? We get a loss from the comparing the probability that the graph generates, the arithmetic circuit generates, and the actual probability that should be the correct one. And this loss can go through the circuit because we have just multiplication and addition, and all of these are differentiable. We get to the different components of the diagram, and we get individual loss for that.
Okay. And another question, more technical on that, is that do you have any vanishing gradient phenomenon because you have multiplications of probabilities? So you may have, I mean, depending on the number of literals you have in the rules, you may have very, very small numbers there because you multiply.
I think you are asking me whether we're losing probability mass, right?
Yep.
So these systems, correct me Nico if I'm wrong, are designed in a way not to lose probability mass.
Okay.
Nico, am I correct? So
Okay.
you don't lose probability mass. The probability that you are calculating at the end for each different outcome, all of these add up to 1. So you don't have cases that are not accounted for.
Okay. Okay. So, yeah. Great. Okay. If there is not any other question, then coffee is waiting for us outside. So there's one more question there, maybe. You were late, but it's okay.
Hi, thank you for your presentation again. I would like to ask what determines the states, the number of the states of the automaton, and the arrows between them. Thank you.
Very good question. We try to go for the simplest possible automaton that will work. That's the honest answer. The states do not necessarily mean something. They don't have semantics. They just provide sufficient expressivity for the automaton to capture the patterns that should be captured. But we do have the logic. Nico, I think you need to correct me here. How do we get the transitions and the... In the case that I showed, that the automaton was learned from data. That's why I mentioned that we try to get the simpler automaton. So given some data, we learned an automaton that was the smallest one that could capture the data that was trained from. But if we have...
I don't have much to add. The number of states is indicative of things that happen sequentially. So if you have 3 states, for example, there is a maximum of 3 events that can be repeated, and then there are self-loops in the states, which means that you can have the same event repeating multiple times. Regarding the logic is learned from one individual time step from all the knowledge that is present in that time step. So the logic is learned known in a time-wise fashion. You don't factor in the temporal dimension when you learn the logic. That's what the automaton is for. The automaton and the transitions is for time, the logic is for static states.
But if you have manually provided knowledge and you want to translate that into automaton, then the automaton would have a specific number of states that corresponds to the manual.
Yeah, if you say my pattern is A should follow B, which should follow C, then you should have probably 3 states.
So I don't know if maybe the answer was too complex, but what we're trying to say here is that there are 2 cases. The manual case where the states correspond to the patterns. You remember the patterns that Alex was showing earlier? So we need to translate this into an automaton, and the states map to the pattern that is described by the logic. But then we have another case where we learn the logic or the automaton directly from the data, and there we just try to find the most compact automaton for the training data.
Okay, thank you very much.
Okay, I guess there are no other questions, so we can enjoy coffee and continue with the last talks. Thank you.